Good day, everybody who is now online to the webinar of the EO Africa project. My name is Wolfgang Wagner. I'm from the Vienna University of Technology, or shortly TU Wien. You see the web address here. And the webinar today is about global flood monitoring and surface soil moisture anomalies. So if you have any questions, there's you will find on the Zoom bar that there's a question and answers tab. So if you go there and if you type in your question, I can try to answer them during the talk or after the talk. So please use that function, the Q&A function. So this talk today is the 9th webinar of the EO Africa project funded by the European Space Agency. And you see here all the talks that have been there before that have, for example, focused on how to use cloud computing capabilities for doing the analysis of Earth observation data, or how to access them and download them to your own software service. And there also have been a presentation that has quite a familiarity with what I'm discussing today. There has already been a topic on using flood mapping using Sentinel-1 data, where you were shown how to download Sentinel-1 data and analyze the data at your desk. Yeah, today we look more at a different approach where you already download, analyze data and use it in the applications. Maybe also let me point out that there will be some upcoming webinars that are also giving 2 more by the TU Wien. And another upcoming webinar closely connected with today's topics will be on about surface soil moisture products at continental scale, where we'll show how to use Sentinel-1 for surface soil moisture estimation. And then we also will have a webinar on drought monitoring case studies in Africa. I hope everybody hears me well. If not, please let me know over the question and answer bar. So what do I want to present today? What is the idea behind this webinar? Well, in this webinar, I combine the ideas of observing soil moisture, so the water stored within the soil, with the capability of observing flood events from Earth observation data. The big difference between the 2 techniques is that soil moisture is most readily observed at a rather coarse spatial resolution that is roughly in the scale, say, between 6 and 50 kilometers, depending on the sensors you're working with. But with the big advantage that we have nowadays sensor systems that give you a very good temporal coverage, so that within 12 to 48 hours, we have new observations. Also, the modern satellite systems are such that we can analyze the data in near real time. Yeah, so with those data, you can check if there are, for example, exceptional wet conditions at the regional scale. And if yes, if the answer is yes, it could, for example, be extremely wet. Then it would be indicative that, well, if the wetness continues and there's additional rainfall that leads to flooding. Of course, the other extreme would be if there's too little soil moisture, that would be a drought situation. And once you have the regional overview, you can then use high-resolution Earth observation satellites to zoom in, to, for example, to ask the question in the case in the wet scenario, if existing water bodies have expanded or if there's even inundation in the surrounding areas of the rivers. When you approach the topic, if you want to work on those things, you need to answer first the question at which data level you want to work. And here on this slide, you see the different data levels we have in Earth observation. We call them level 0, level 1, level 2, level 3, and higher. And the level 0 data are typically what we refer to as raw data. So these are basically digital numbers representing electrical quantities as recorded by the Earth observation sensors. The next level are geometrically and radiometrically pre-processed data. So it's typically the level that you can receive from the space agency, like European Space Agency, or from EUMETSAT, or from NASA. Yeah, you would typically refer to those level 1 data as images. But in a more generic sense, it's just data representing some geophysical quantity like backscatter or radiance, etc. At the next level, you have those data interpreted into and analyzed and represented as geophysical variables like soil moisture or flood extent or leaf area index or any other of these variables. You could refer to those as retrieved data from the Earth observation data. And that at a higher level, you would start combining data from different satellites, or for example, combining satellite data with model data to produce value-added data products. So in a way, combines data products. Maybe as a note, this way of how I defined here the levels is a physical view of the definition of the levels. You often find that, for example, people speak about a different level if they have just used a different spatial and temporal grid. But being as a physical scientist, I'd rather prefer the physical view of this definition of the levels. And if you want to now work with soil moisture data in order to observe floods, the question is, with which data would you like to work? You could decide to work with images and derive soil moisture conditions and the flood extent yourself. Yeah, what would this require is that you would have an expert knowledge on the analysis and processing of the Earth observation data. As you're also typically dealing with a large amount of data, you would either have a powerful infrastructure, IT infrastructure, or you would use cloud platforms, as for example, the ones provided by Europe, or for example, by Google or by Amazon. The advantages when you work with images is that you have full control of each processing step. Yeah, so you have complete insight in how you transform the data from the original image to the final product. And of course, if you have this approach, you can adapt your algorithms to the local conditions, which typically improves the results. A disadvantage of that approach is that it enforces a strong focus on specific sensors, because in theory, it sounds nice that people say, well, you can use all data. You can use data from Landsat, from Sentinel, from 1 and Sentinel 2, you can use Pulsar and whatever. But in the end, each of these sensors has its peculiarities, and using each sensor requires some expert knowledge. So yes, in principle, you can use all the sensors, but it requires quite some work for you to get into each sensor, get the data, and prepare them such that you can use it. And of course, with this approach is that you typically have to deal with large data volumes. So working with level 1 data is not easy. The alternative approach is that you work with retrieved data, so level 2 data or maybe even higher level data. Yeah, so in this case, the prerequisite is that you have a generic understanding of what Earth observation data is, and you must have a capability to judge the strength and weaknesses of each data stream. The advantages of that approach is that you essentially then access data that are processed by domain experts. They will then work on a global level, but they have very specific knowledge on the sensor. They cannot maybe not tune the algorithm so nicely on the local scale, but they have an overall very good understanding of the strengths and weaknesses of each sensor. As a user, it will also be easier to work for you with multiple data streams because, yeah, you already have data sets that are easier to handle than just the images. And it will also be more easy for you to directly link those data to geophysical models, for example, hydrological models or runoff models. A disadvantage of that approach is that you will sometimes struggle to understand the properties of the data. So you will get a data product. You have maybe not enough insight to understand how the data are being transferred from the original sensor measurement to the final data product. So you might struggle to understand this. And of course, there's a certain then reliance on external data providers. Let me first give an overview on what kind of satellites you can use for doing soil moisture and flood monitoring. Yeah, here you see 2 or 6 sensor types. And on top, you see sensors that are working in a so-called L-band at microwave frequencies. So L-band is a rather long microwave frequency in the order of about 20 centimeter wavelengths. And the advantage of working with these long wavelength sensors is that they can penetrate into the vegetation and into the soil quite deeply and give you a rather strong response to changes in soil moisture, and also a very good response to like the presence of open water. At the sensor at the lower level, they work in a so-called C-band, which is a shorter wavelength at say in the order of 6 centimeters wavelength. They also are still very sensitive to soil moisture and flooding, but not so strong. So a bit dampened sensitivity to the 2 parameters of interest. On the very left of the sensor types, you see radiometers. So these are passive microwave systems that observe the naturally emitted microwave radiation from the land surface. Say 2 flagship sensors are here: the SMOST, the Soil Moisture and Ocean Salinity mission by ESA, and the EMSA-2 mission by the Japanese colleagues. They observe the brightness temperature measurements at a resolution in the orders from, say, 20 kilometer up to 50 kilometer. So rather coarse resolution measurements here. But again, with the big advantage of having daily measurements. In the middle, you see systems that either active only or active passive. Very famous is the mission here in the middle. That's the Soil Moisture Active Passive mission operated by NASA, that had both a capability for observing active measurements and passive measurements. Unfortunately, very soon after launch, the active channel failed. So at the moment, we only have the passive channel that gives you a native resolution of about 36 kilometers. And down here is the ASCAT, about which you will hear more. So the ASCAT is here the sensor. We have here 6 antennas pointing to both sides of the satellite track. It's operated on a so-called METOP satellite. And this sensor gives you a resolution in the order from 15 to 25 kilometers. Again, with a very good temporal coverage. And last but not least, on the right side, you see scintillating aperture radar systems. On the bottom, you see first the Sentinel-1 mission that has been providing operational data since 2014. And on top, you see an exciting new mission that will be launched by NASA and the Indian colleagues next year, the so-called NISA mission. It will give us both L-band and S-band measurements. And it will be also used for doing, for example, soil moisture monitoring, flood monitoring, ecosystem monitoring, and many more applications. Yeah, all of those sensors you can use for monitoring soil moisture. In order to use flood monitoring, you only use the SAR data, because only the SAR data have a fine enough resolution to give you a meaningful water body product. So what are some generic properties of microwave measurements? One big advantage of those systems I just presented to you is that they operate under all weather conditions day round. You also don't have any problems with clouds. So whenever there's a measurement taken by the satellite, you can use the data for your application. A very big advantage compared to optical systems, where cloud coverage obviously hinders the acquisition of the images. Obviously, if you have a flood situation, not being dependent on cloud coverage is a good thing. The other big advantage of microwaves is that we penetrate deep into vegetation and soils, so we can get some subsurface information It's beneficial in most cases. I'll show you with this presentation, also focusing a bit more on the African case. It can also make things more complicated. I will show you some of the effects later on in the talk. And another very big advantage of microwave measurements is that they're very sensitive to the presence of water, because water molecules have a dipolar structure where there's where you have a dipole moment where the positive and negative charges are separated, and when there's now an external electromagnetic field being applied, the water molecules start wobbling, basically reacting to the external electromagnetic field and modifying it. Technically, we basically then say it's that the dielectric properties are very high of water. Yeah, so here on the right graphics, you see the dielectric properties, both the real part, which stands kind of for the reaction of the capability of the medium to react to the applied external field and modify it. And there's also an imaginary part to the electric constant, which basically tells you how much this material absorbs in terms of the microwaves. And you see, you go here for microwave frequencies from about 1 gigahertz to about 100 gigahertz. So below about 10 gigahertz, the real part is very high, meaning that we get a very strong response from water at those frequencies. Here you see the frequencies indicated by the blue line of Smallson's map. And here you see the frequency where the advanced spectrometer and Sentinel 1 is operating, and here the one of AMSA 2. If you go to frequency much beyond the 10 gigahertz, you lose the sensitivity to the response to the water molecules or soil moisture, for example, in the soil. Yeah, and you cannot measure that quantity that easily any longer. Also very important for our applications is that microwave measurements are extremely sensitive to geometric structure, so the roughness of the objects that you're sensing, if it's now the surface or if it's like the vegetation. Yeah. So imagine that you're observing a land surface that doesn't have vegetation on there. So you might, for example, see a bare soil, or you may see an asphalt road, or you may see a water surface. If you have such a situation, like a plain surface, a very smooth surface, then you may have the incoming radiation from a satellite, and the radiation is being scattered forward in a specular direction. It's like the mirror reflection. Another situation is then if the surface becomes very rough or almost perfectly rough, then you have an incoming radiation and you have an almost equal scattering in all directions. And of course, there are intermediate cases between those two idealized conditions, that you have like a strong forward component, but there's also scattering in all kind of different directions. So that would be the most realistic scenario for most of the surfaces that we have. Important to know is that the term surface roughness has always to be seen relative to the wavelength. So if you're working at the wavelengths of 20 centimeter, you can have roughness variations in the order, say, of millimeters, several millimeters, and that surface will still appear smooth to you. Yeah, so imagine you're sensing with 20 centimeter wavelengths a sand beach, and the sand is very smooth then for that wavelength. On the other hand, if you would be looking with optical, like with optical instruments, where you're working with wavelengths in the order of micrometers and submicrometers, then this surface would appear very rough to you. So where do we have then an application here? A very first simple application would be the mapping of open water surfaces. Yeah, so imagine a situation where you have like a soil that has a certain roughness that is even rough for the microwave scattering. Yeah, then you produce a rather high backscattering, a rather high response. And now imagine this soil surface is being inundated by water, and then this rough surface becomes suddenly totally smooth for the signal, for the satellite. And then suddenly you have low backscatter. And this is what you see then in those Sentinel-1 or SARs or in any other SAR image, that in case of flooding, you have those dark areas because all the radiation that is coming from the SAR satellite is scattered in the forward direction and nothing is coming back. So the response is a very, very low signal compared to the surrounding areas where you still have the scattering from bare soil or vegetated areas. This image here shows, for example, a Sentinel-1 image that was taken on the 13th of January 2019 over Queensland. In my talk, I want to focus just on the two sensor systems, the METOP ASCAD and the Sentinel-1 SAR. The advantage of those two systems is when I can combine them in a talk, because basically they measure the same thing, that both measure backscatter at a frequency of around 5.2 to 5.4 gigahertz. So there's hardly any difference in terms of the frequency. They also measure the same polarization in the so-called VV polarization. Sentinel-1 would also measure in the VH polarization. The major difference between them is in terms of the spatial resolution and in the repeat coverage. Yeah, so the ASCAD instrument measures at a very coarse resolution of say 15 to 25 kilometer. Right now we sampled them on a grid of 6.25 kilometer. But the advantage is daily global coverage that is above 80%. With the Sentinel satellites, we achieve a resolution in the order from say 10, 20 meter. We work with a sampling of 20 meter because then there's already a kind of a smoothing of the images that are affected by specular with it. Yeah, and another disadvantage of those data is they don't come daily, but there's a repeat coverage in the order, say, from 3 to 12 days, depending on where you are in the world. Yeah, until the end of last year, we were fortunate enough to have like 5 satellites flying, 3 METOP satellites, until the end of 21, sorry. We had 3 METOP satellites. At the moment, we only have 2, METOP B, which was launched 2012, and METOP C, which was launched 2018. But we are already looking forward to the launch of the next generation of that sensor, which is foreseen in 24. With Sentinel-1, we still have the Sentinel-1A that was launched in 2014. That's still healthy and ongoing. Unfortunately, the Sentinel-1B unit that was launched in 2015 was lost in 2021. Yeah, the replacement of a Sentinel-1B was foreseen to be very quick, but unfortunately now with the problems from the launcher side, we can expect some more delay to see Sentinel-1C coming. Yeah, here's an image that illustrates what I just said, is that if you work with the METOP ASCAD, you work with data at a rather coarse resolution, but with a very good temporal sampling. This is the daily global coverage that you achieve if you use 2 ASCAD instruments. Unfortunately, there's still some voids that you see here, these diamond shapes that are over Africa or near equatorial regions. And also here, there's a second band here. That's kind of related because the phasing between the 2 satellites is not optimal. This could be optimized for us. Unfortunately, this is in conflict with the interests of another user community from another instrument, For them, it's optimal coverage if the satellites fly in that formation. So we need to live, unfortunately, with those gaps that are sometimes there. So that could mean if you, for example, a user in Africa, you could have 2 or even 3 acquisitions per day, but the next day you don't get any. So there's a certain irregularity in the measurements. With Sentinel-1, on the other hand, we get a very high spatial resolution, but in order to get a complete global image, we need to collect data of a very long time span. Also, the Sentinel-1 is very strongly depending on the orbital patterns. So to get then an image that is kind of clean and is not showing too many orbital effects, we actually need to collect quite many data, as we did in this work, where we used 2 years of Sentinel-1 acquisitions to produce a global backscatter mosaic. Yeah, for this exercise, we processed over 500,000 Sentinel-1 images. We used over a petabyte of total disk space to produce a rather clean mosaic of the world surface at the resolution here at the sampling of 10 meters. Yeah, for most of the world surface, you see that you hardly see any stripings. Unfortunately, in those areas where coverage is not that good, like for example here in Africa and Southern America, you still see some stripings left. But nonetheless, you can, if you're interested, please go to that website here, and you can zoom in and at great detail as those maps and try it. You know, it's a really nice overview of the properties of these data sets. We also published this data set here in the journal Scientific Data, and if you go to that web page, you will also be directed to a repository site where you can actually download the data yourself and work on it locally on your disk. To give you an impression of this data set of an area, here this is an example from India. This is an agricultural area in India. There are not too many, not too many, it's not a colorful image. So these intermediate gray colors basically show you a mixture of agricultural areas and forested areas. The brighter areas here are urban areas or smaller villages. And very interestingly here for that area here in India, you see those many black areas that are either reservoirs or natural lakes that have been created in order to have enough water for agriculture and for the people. So you see the whole landscape is being dotted with small reservoir lakes for energy production, water for agriculture, water for the people, etc. Now this is the same image, but if you go for Africa, the black areas doesn't necessarily mean that there's water. Maybe let me go back to the very first image. If you look here, for example, in the desert areas, also here backscatter is very low, and the reason is that the microwaves penetrate while they hit the sand surface, penetrate into the sand surface and never come back. So in this case, it's not that the radiation is scattered in the forward direction, but the radiation impinges on the sand and never leaves the sand again. So also there we have very low backscatter. So that if you go, for example, now to an area, here this is an agricultural areas west of Cairo, we see sandy areas here in those black colors, and then we see some irrigated fields here that show up more, higher backscatter because there's both higher soil moisture conditions and there is some vegetation that can be then nicely seen. Obviously, it's not just the vegetation, the agricultural fields that can be seen here, but there are also like houses, and villages that produce higher backscatter. Now, in order to go from those backscatter measurements to a geophysical data product like soil moisture or water body, we need to have a model behind it. So we need to model the interaction of the microwaves with the vegetation, with the soil, with the water surface, in order to give you this geophysical data product with a certain unit to it and with a certain confidence. I'm not going into this modeling step in detail, but obviously you can imagine that irrespective of how complex the model is, it will always be a simplification of a rather, of a beautiful nature and complex nature. So there will always be compromises have to be made in terms of the complexity of our model and interpretation of the data, leading to some uncertainty in the products that we're delivering. Also, when working with these kind of microwave data, you should always be aware that, say, intuition is not a good guidance. Because we humans, we are accustomed to observing our environment with our eyes in the visible domain. And in the visible domain, the environment looks totally different than at microwave frequencies. Now, for example, this can be visualized if we look, for example, here at that wheat field, and with our eyes, we see this kind of a very compact wheat canopy. And you don't really see, if you look from the side into the wheat, you don't see much of the ground, of the surface. But if you look with microwaves at the same object with a much higher frequency, say here on top of, here at C-band at about 6 centimeter, you're actually not seeing the wheat stalks very clearly, but you mostly get a strong signal from the ground surface. So what this image here shows you, incremental backscatter at different vegetation canopy heights. So here's the top of the canopy, and here's the ground surface, and here's shown the incidence angle. So if you look very steep into the canopy, most of the response here comes from the ground. And the more you look to the side, the less signal comes from the ground and the more comes from the canopy. It also depends on the polarization. Here you have BV polarization, and here you would have what is called the HH polarization. So in the case of HH polarization, for this particular wheat canopy, most of the signal would be coming from the ground. Yeah, if we would work now with L-band data as being used by SMAP and the other satellites, that contrast would be even starker, that you get a very weak response from the vegetation canopy and the dominating signal coming from the ground. If you go to higher frequencies, like here X-band, that's roughly around 10 gigahertz, then the situation changes. Then here the vegetation component would already dominate, while the ground signal is very weak. Now, this is a beautiful picture that was taken in a laboratory experiment. Unfortunately, we don't have these capabilities from the satellites, but when we work with satellites, we only see the total signal coming back, not sliced up over the different vertical layers. Yeah, if you would have that situation, the interpretation of the data would be much easier for us. Now, the way we can, for example, use then those measurements to retrieve soil moisture is that we look at time series. Yeah, you could have like a backscatter time series from the advanced spectrometer or from Sentinel 1, like shown here for a certain year. And we see very strong variations from day to day that are short-term changes that are caused by changes in the electric properties. Yeah, if backscatter is high, that typically refers to a wet soil. If backscatter is low, that typically refers to a dry soil. Also visualized here in the colors. So brown colors here mean it's dry soil, blue colors means it's wet soil. We need to model the seasonality of the vegetation, obviously, because the more vegetation is there, then it has an impact on the backscattering coefficient, so it takes away sensitivity of the response of the backscatter to soil moisture changes. And with ASCAT, we are very fortunate that we have a multi-incidence viewing capability with which this can be modeled quite nicely. But in the end, once we have this variability, we can estimate the soil moisture content by just looking at the current measurements with respect to like a dry soil, backscatter from a dry soil, and here scale with the sensitivity. Yeah, and doing this for each pixel then allows us to get a global image of soil moisture conditions that you can also receive locally. So here's an soil moisture image acquired by the ASCAT sensor in one ascending or descending node. And that image is taken from yesterday. So this is an orbit track that was acquired about at 2:10 with the METO-B satellite, with here the sampling at 12.5 kilometer resolution. So again, brown colors means rather dry conditions, blue colors means rather wet conditions. And you see here in Africa, we have the track here. Well, dry conditions in the northern parts and wet conditions here in the southern parts, southeastern parts. There are some areas where you don't see any data. In this case, it's not because there aren't any data. There are data, but say if there's snow or frost, as we currently have in much of the northern hemisphere, particularly northern Canada or northern, like here, Northern America, and here in Russia, then we can't do soil moisture retrieval. So we need to master data for snow and frost. That's why we don't show any data here. Let's go back to a time series impression of those data. Obviously, if you have a time series of soil moisture, you can look at anomalies compared to a climatology. So we, for example, calculated the climatology of the last 10 years and then calculated the current conditions, compared them with the climatology, and then you have either wetter conditions than normal or drier conditions than normal. And what you can see here from the plot is obviously soil moisture is a very dynamic variable, where you can have a very quick change from wetter than normal to drier than normal. So exceptional conditions really then only occur then if you have like these wetter conditions for a longer time period or drier conditions for longer periods. Now this time series here is taken from an example from Austria, an area where I was grown up. That is typically very wet. But in 2015 and 2018 were exceptional years, extremely dry for Austria, and we had big impacts on the later crops like maize. Now bringing again this kind of time series plot on a spatial map, so showing the anomalies of soil moisture. We've prepared here two maps, the one for July 2021 and here one for July 2022. You see here when you make those global plots, there's always around the world areas where you have drier than normal and wetter than normal conditions. So it's not straightforward to say just because it looks wetter than normal, there's a flood going on, and it doesn't necessarily mean that it's drier than normal, that we have a drought going on here. But those maps that are updated, can be updated daily, can give you a first warning to look more closer. Do we have a critical situation that may lead to a flooding, or vice versa? If it's too dry, does it lead to a drought situation? Yeah, and in the examples then I picked up here, in July 2021, we had devastating floods here in Central Europe, in Germany and Belgium, a little bit also in Austria. That was big news here in Europe. And the year afterwards, in July 2022, we had two dry conditions in Europe. We also had a drought in China. And we had here this massive wet conditions over the Indian continent, in particular over Pakistan, that led to disastrous flooding. Yeah, let's have a look then At the case from 2021, July over Europe. So here we had this exceptionally wet soil conditions accompanied by rainfall that kept on falling, very high intensity rainfall, and that led to a disastrous flooding along some of the rivers in Germany and Belgium. And then you can take a Sentinel-1 image and you see basically the typical flooding signatures from the data. So very low backscatter and the surrounding areas, agricultural areas and urban areas. The other big example was the Pakistan flood, where there has been for weeks steady rainfall pouring in from the south into the valley of Pakistan. I'm sure you heard about this disaster, and well, we have done an analysis of all Sentinel-1 data that were available for that period, and here you see the assessment of all the data that were acquired between the 18th of August to 23rd of September, how long certain pixels were flooded within that time. And very light, this lighter reddish color shows you like pixels that were flooded only shortly, but then there were also pixels that were flooded all the time over this period. Overall, if you sum up all the area that was inundated during that time, you would come up with an area of the size of whole of Belgium that was flooded. In the news, basically, politicians said that about a third of the country was underwater. You know, taking this statement literally is not true, because the area was smaller. There was still lots of ground that was not flooded. But in a way, in terms of its impact on the people, I would think this was a fair assessment that really a third of the country was extremely hit by the flooding. What's also exceptional for that flood was that still, if you looked at the images that were taken in December, we still saw lots of areas that were flooded at that time. So weeks and months after the flooding, it's just water that ran into areas that, you know, they didn't have enough pumps to get the water out. So even then, it was like 20% of the inundated areas were still standing underwater a month later. If you're interested in the analysis of the data, I can point you here to that paper that was published as preprint on the Eciosphere. Yeah, maybe a next example was flooding in Nigeria last year in, say, September-October framework, where we saw that from the ASCA data, we had very massive wet conditions at the end of September, and then rain started, well, kept on falling, that led then also here to flooding around major river systems here in Nigeria. The extent was not as large as for Pakistan, but obviously still extremely large areas were flooded at that time. So again, you see that by looking at soil moisture anomalies, you get a first hint where something may be something going on, and then you can zoom in with the SAR data to look at more details, and then you might find those areas that are affected by flooding. The Sentinel-1 images we took to a large extent from the so-called Copernicus Emergency Management Service, from the Global Flood Monitoring Component. This Global Flood Monitoring Component is a new service of the Copernicus Emergency Management Service that was put into operation about 1.5 years ago. So it's still a rather recent service, but now we see very nicely how it's working. Yeah, the idea behind that service is that we are not taking individual images and then produce some flood maps. The idea behind that service is that you take all the incoming Sentinel-1 images and process them in near real time, irrespective if you know that there's flooding or no flooding. The big advantage is that you don't lose time from, well, saying, oh, there could be a flood, or let's look into data. But no, you process it all the time, and immediately you get an output seeing if there's a flooding or not. So as long as we had Sentinel 1A and Sentinel 1B, well, we processed 2 data in fully near real time. At the moment, we are down to 1 satellite and hoping that Sentinel 1C will be launched very soon again. A novelty of that service is also that we use 3 different flood mapping algorithms. And the output product is quite a complex, I would say, scientific data product where we're not just showing the flood extent, but we also give you estimates on the uncertainties of the data product. And we give you exclusion masks to say, well, here you shouldn't, well, here we can't use the data for doing the interpretation. And we also give advisory flags how reliable the data are due to changing environmental conditions. Yeah, this graphic here, this colorful graphic here, shows you an analysis of the coverage that is being achieved by Sentinel-1. Yeah, so those purple colors show areas where there's very good repeat coverage in the order, say, from 1 to 3 days. In Europe, we get every 1 to 3 days, we get a new Sentinel-1 image. So there we have very good capability for observing changes in the water. Over Africa, unfortunately, coverage is not that good. It's still okayish in, say, in agriculture, in tectonically active areas and in agricultural areas, but it's suboptimal, particularly like in the desert areas and forested areas. Yeah, here comes basically the limitation that the instruments cannot be switched on all the time. So say 1 Sentinel satellite makes an orbit around the Earth in about 100 minutes. And from these 100 minutes, the satellite can be switched on 30 minutes. So the European Space Agency needs to make a decision when to switch on the sensor, when not. This explains the rather unequal coverage on a global scale. In terms of the algorithms we use for that service, there's one algorithm that has been developed by our colleagues from the German Aerospace Agency, the DLR. One algorithm from a group that is very well known for their algorithms for doing flood mapping from SAR data from the Luxembourg Institute for Science and Technology, LIST. And the last algorithm is for my team, the TU Wien algorithm. In terms of their approach, they're very different. In that sense, also very complementary to give us information about flood. And we learn a lot from looking at 3 different algorithms. And from this, we can deduce how to improve the algorithms further. Yeah, for example, the DLR algorithm is a kind of a more classical water flood mapping algorithm that uses then fuzzy logic with post classification and region growing to have a good delineation of flood extent. The LIST algorithm compares essentially 2 images and then also done with hierarchical split-based approach and then also does some region growing. And our algorithm from TU Wien is a Bayesian classifier that we'll show you in a minute. Yeah, and in order to give you a flood estimate in the final product is, we say that, well, at least 2 algorithms must agree. Yeah, so for example, you would have a situation of a flood that occurred in China, and then we can look if say 1 algorithm says that there's flood, or 2 algorithms say there's flood, or 3 algorithms say it's flood, and then you would have the ensemble giving you a final map, where this is a best automatic guess of where flooding has occurred or is occurring. Here's another example from Madagascar, from the 3 algorithms from DLR, LIST, and TU Wien. And that image already shows you some additional information. It shows you not just the flood extent areas, which are shown here in red. It also shows you that we mask in the products areas where we either cannot retrieve water bodies or because like the topography doesn't allow that there would be any water. So we provide, along with the estimated water extent, we provide a mask and exclude those areas from analysis. For example, we call them here no sensitivity layers, low backscatter layers, topographic distortion, or radar shadows. But overall, you see that the three algorithms here in that case agree very nicely. Okay, so if you're now interested in using this data, you could, for example, become a user of the GFM service or the Copernicus Emergency Management Service. And they have a user interface that is called GLOFAS. There was an interface they already developed before for modeling river discharge, for example, or like the more traditional modeling approaches starting from rainfall products. Now they've also integrated within that service these new novel Sentinel-1 datasets. Yeah, and if you register to the website here and get access, you could, for example, see all the Sentinel-1 images that were acquired yesterday on the 13th of February 2023, and you would see the global coverage. Again, unfortunately, we only have, at the moment, only one Sentinel-1 satellite, so the coverage isn't too good. If you look here, for example, of Africa, it's actually quite poor. With a second satellite, it would already look better. So in that sense, like if you have a very fast flooding, the chances that you miss it are unfortunately quite high. But say in this case, in a way, for that presentation, I was lucky enough that there were some images acquired over Mozambique, where currently a flood is ongoing. And in the next slides, I keep on zooming into that situation. So here's the first overview of how many Sentinel-1 images you get. Then you could also switch on in that, well, you could start zooming into Africa, and you, in addition to the Sentinel-1 images, you could switch on like an indicator that says if the predicted runoff is higher than normal. Yeah, so those kind of along those river networks, we see that there was obviously high intensity rainfall in the area that led the hydrological model to predict that there's higher than usual river discharge. That's shown on those colors here. You can also look at soil moisture. Yeah, so as we did before. So taking now another node from the ASCAP data, also acquired yesterday, we see that essentially here in that part, and this southeastern part, the soils are saturated. So every rainfall that falls now on top of those saturated soil goes into runoff. I see that first questions are coming in. Please allow me to first finish the presentation. I think it's easier, and then I will try to address all questions. Then we can zoom in further. Now I zoom in here to those areas covered by the Sentinel-1 images. Again, here I have now the river network simulation switched on. So it's still the high river discharge pixels. And now the flood extent maps are shown in this bluish, light bluish colors. You see here that the meandering along that river system here. Yeah, and this is again an image from yesterday, and this is just a very recent feed here by this website saying that we have this flood situation currently going on in Maputo and surrounding areas. Here's Maputo, and here are the surrounding areas. Yeah, and we can zoom in then further and relate them to the land service feature. Now I switched within the GLOFAS tool from a simple gray map, and we use now a Bing aerial image with labels, and then we can much more easily interpret those flooded areas close here to that river system. In this case, I also switched on the reference water mask showing us permanent water bodies and seasonally occurring water bodies to distinguish between flooding and seasonal occurring water. Okay, and now basically I tried to show you now some examples that hopefully illustrating you that we have a very powerful technique here. But as in with every technique, some things work nicely and other things don't work that nicely. Let me explain again how we do this flood mapping algorithm, and many questions that I'm seeing that are coming in. They're basically questions how do those flood mapping algorithms work. So essentially what we are looking for is a change to very low backscatter in the Sentinel-1 images. So this very low backscatter is in the order, say, of -18 dB. Then it's characteristic for open water. Yeah, say a good thing is that if you look at the backscattering signals from calm open water, they are the same everywhere around the globe. If we have a calm ocean surface or if we have a calm water body, the backscatter is always very low. And it's even lower the more I look to the side of the satellite. So if I look at steep incidence angles or at the near swath, they are in the order of, say, of -16 dB. And if I look at higher incidence angles, they then at the order of -20 dB. So I need to take into this account that depending on exactly the incidence angle, there's a certain change in the signature of a calm open water surface. So ideally, I'm looking at the situation that I first have high backscatter, then there's water coming, the water is smooth, and then I have a very clear signature, and I can very easily say, here's the open water. Now again, reality is more complex. It becomes already more complex if I have vegetation. Yeah, for example, if there's like high vegetation and then water is coming from below, we may have a situation that we have double bounce effects between the vegetation canopy and the water surface, in which case actually backscatter may go up and it may not go down. Only once the water reaches such critical height that most of the vegetation is being submerged, then again, I would have a very clear water signature. But say in this situation, most likely you will not see the flooding, unfortunately. What we do in our algorithms that was published here in that paper last year in remote sensing, and where the first question was referring to, we use an approach that we use historic information about the behavior of backscatter for each individual pixel. For example, this would be, I don't know where this pixel is, but we would see here rather high backscatter between -10 dB and -5 dB, a certain seasonal variability. And that's the expected behavior for the pixel. Yeah, so if we take then, for example, a measurement here that is higher than this normal expected backscatter, well, we can be pretty sure here's no water. On the other side, there sometimes there may be an outlier that is much, much lower than here this expected behavior. Then that would be a flood signal. So what we do is we characterize the expected backscatter of open water through a probability distribution function. The same we do for the expected backscatter from the land surface. And then we compare in a Bayesian approach, the two backscattering functions. So here would be, in that situation, here would be the expected water signature. Here would be the expected signature for land. The green one shows us the measurement taken here. So very clear, we are very far away from the water signature, and we can easily decide that this is not flooded. For this measurement here, the measurement basically is here. So very clearly on the side of the probability distribution function of water. So in this case, it's a clear case that we have here flooded pixels. The most problematic area for this algorithm is obviously here, where the likelihood for water signature and length backscatter signature is the same. So here we cannot really decide, is it water? So here we may have some confusion between the classification of water and non-water. So in principle, that looks very simple, but you know, again, nature is very complex, so many things could go wrong. One thing that can go wrong is that there's many surfaces that also have very low backscatter. You can call them water lookalike areas. So a typical example would be like an airport, the runway, the tarmac, that looks very smooth for the radar. So looks more or less like a water body in terms of very low backscatter and extent. I already showed you the case of the sand deserts. Also, the sands basically swallow the microwaves. Nothing is coming back. Also, those look as if they would be water. In our regions or in UK, there could be some grasslands that have this kind of very low backscatter behaviors. In mountainous areas, there could be radar shadows that also are very low backscatter that can be confused. So these are static water lookalike areas. Then there's also dynamic areas where at some point in time over the year, it could become very low backscatter. Like for example, over agricultural fields, shortly after sowing, fields are often so smooth that they also produce very low backscatter. Could also be the case in Africa, not so much, but like in Europe and Asia, big problem. Like if there's snow and the snow is thawing, then we have a wet snow surface. It also may produce low backscatter. Also, when the soils freeze, it can be low backscatter. So unfortunately, there's also like many situations where we can have backscatter that is as low as for water, which may then cause problems with false positives. And if you now think about the GFM service, where we basically analyze each image in a fully automatic way, these kind of water lookalike areas are particularly problematic for scenes that do not show flooding. Yeah, another problem is when I have no sensitivity to essentially the appearance of water. This could be, think about a dense forest, and below the forest canopy, like water starts accumulating. I will not see through. So I think about dense tropical forest, and water is rising below. We will not see this with the SAR data. And the same over urban areas. There's lots of complex interaction signals between the buildings and the water surface. Also, that doesn't lead to necessarily low backscatter. So these kind of no sensitive areas are problematic in flood scenes, and these may cause false negatives. So in a sense, with algorithms, if it's now fully automatic, or even if there's like interpreted by land, these are physical limitations. So you can never be 100% perfect in your image. But of course, if you do a manual interpretation, you can put all this knowledge of the environmental conditions on the side into the algorithm to correctly interpret it. What we try to do in the global service is that along with the flood product, we also provide exclusion layers where we exclude areas for whatever reasons we believe is not possible for map water correctly. And I show again the same image from before of the ongoing flood right now in Mozambique. And you see with the gray areas, actually quite a lot of areas have to be masked due to reasons, for example, because they're urban areas, because there's dense vegetation. We also include here like a hunt index that says, well, in this topography, there cannot be water because it's too steep, or because there's low backscatter. Yeah, so that needs to be accounted for when interpreting those data. It's not, we are not doing classification everywhere, but only for the areas where there's very good physical reasons to believe that there you can do a classification. Yeah, I've now talked a lot about problems, and let me, in the end, address a particular interesting problem that is occurring across Africa. Is in the beginning I said that a big advantage of microwaves is the long wavelengths that let us penetrate deep into the soils. Now, in most situations, this is an advantage, but it can become a disadvantage if the soil is dry. Yeah, in this case, when the soil is very dry, the microwaves, if it's now L-band or C-band, they penetrate several decimeters into the soil. And if there is no subsurface feature, like if it's a homogeneous sand layer of sand that is thick, nothing will come out again. So these are the low backscatter areas that we have already discussed before. But there's a more tricky problem is if, say, there's something below the sand, like, for example, there's a rock below the sand or stones below the sand. Then I can have the situation that, again here, that I have some soil or sand below rock or above rock, and here some stones in the layer of sand. Basically, I always get a signal here from the top. But say if the layer is very dry and the radar signal can penetrate deep to the rock, I also have a signature from the rock. Now imagine that this layer of soil is thin and the signal from the rock is very strong. Then basically the received signal from the sensor is dominated by the signal from the rock. Now imagine you're adding some water to that kind of substance. Then the signal, the microwaves would be dampened a lot while going through the layer of sand, wet sand. So the signal from the rock would go down and the signal from the top would go up. And now this interplays between the two factors can give you a very different behavior. Yeah, so the typical behavior we have over most of the world is that if the soil moisture content goes up, the total backscatter goes up, because there's not much penetration into the soil and subsurface contributions are very low. But in some desert areas, it can totally turn around, that the dominant scattering feature is the rock below the sand layer, in which case I start to have a negative correlation between backscatter and soil moisture. So the wetter the soil, the lower the backscatter is, contrary to all expectation. This is not an example from Africa, but somewhere in Saudi Arabia, where you see here a modeled soil moisture estimate from an American model. And normally you would expect backscatter to behave temporarily like this blue line. If you look in this case at the Metov-Ascot backscatter time series, you see the behavior is flipped around totally. So it's a negative relationship between backscatter variability and soil moisture variability. So a clear case for dominant subsurface scattering. And to make things even more complicated, obviously you don't need to have these two extreme cases where the signal is always dominated by the surface or the signal is always dominated by subsurface scattering. You may have mixed scattering phenomena that say this subsurface signals only become apparent when the soil is dry. And the normal expected behavior is when the soil is reasonably wet. So during some part of the year, you would have a positive correlation between backscatter and soil moisture. And here at the dry edge, you would have a negative correlation. And this is already now my last slide on this one. These kind of anomalies obviously follow the seasonal cycle of the climate. So if we take, so these images show when when we here on this edge here, when there's a negative correlation between backscatter and soil moisture. When there's negative correlation, then we see here this dark red colors or even black colors here. And if we have these yellowish colors, the behavior is as expected. So in March, when the intertropical convergence zone is starting to move upwards, here we already have wet soils. We don't have any subsurface scattering signals. But now we start moving further north, the rainfalls, and in September, basically, most of those areas are wet here, and everywhere where it's wet, we don't see the subsurface signals, but as it was dry, we strongly saw them. And looking to the south of Africa, obviously it's the reverse behavior. So when we have the very dry conditions here in September, in this month, we have the occurrence of subsurface scattering signals here, while in March, when it's reasonably wet, we don't see it. So please, if you do an interpretation of Sentinel data or ASCAD data of Africa, please take that in mind that during very dry periods, the behavior can change and not follow the expected behavior. So, yeah, my conclusions would be that if you decide to work with level 1 backscatter data, obviously I'm a remote sensing scientist, so I like it very much, and I like understanding what the data do, but it's indeed not always straightforward of how to interpret the data. Also not very easy to handle the data is because they don't come as analyzers ready data or as simple to use data cubes, but they come in this kind of orbit geometry. So you need to do lots of pre-processing steps to be able to analyze time series. We're also dealing already with very big data volumes. So even if you focus yourself to regional analysis, you quickly work with terabyte of data, and processing each scene can take quite a long time. So very clearly, working with level 1 data, backscatter data, is not simple, and you need quite a lot of expert knowledge. So if you're more a user and a non-radar expert, you may be better off if you start from really available higher level data sets like the Sentinel-1 flood maps I've shown or the ASCAD soil moisture data I've shown. You get the data from the Copernicus services and the EUMETSAT satellite application facility in support to hydrology. Yeah, and with those data come in fully near real time. So for the HSUF, the soil moisture data become available 3 hours after sensing, and the Sentinel-1 flood maps become available roughly 8 hours after sensing, depending on when ESA has finished processing the level 1 datasets. So you can now build near real-time applications. But again, if you build those applications, if you start using those data in a regular manner, you need to understand how the data are being processed to understand the strength and weaknesses in the interpretation. Yeah, and of course, even if you start from the higher level data products, you still need to have some level of pre-processing to make them fit for your application. Where you can already start building in this knowledge of these strengths and weaknesses. So you can do better masking for non-valid and uncertain retrievals. If you want to highlight if there's certain exceptional conditions, you need to bring in, you need to do things like compute climatologies, anomalies, etc., etc. So a lot of work still has to be done, even if you work with higher level data sets. Yeah, last but not least, let me acknowledge that, say, different funding agencies we have. Of course, now for that presentation, I acknowledge the funding from the European Space Agency on the EO Africa project, but also on the Copernicus Emergency Management Service or on the HSAF, and several other projects, research and development projects, where we were able to improve the algorithm and work on the data. So thank you very much for your attention. I hope I was clear and not too fast. And now I switch over to your questions. I go from the top. So the first question was about the article. Okay, that was the article that I was referring to. That was the TU Wien algorithm I presented. Yeah, the next question is if the DLR and list algorithms can be shared. This is unfortunately a question I cannot answer. You would have to or you would have to write the colleagues from DLR and list. I'm afraid that the answer will be no. Yeah, so I don't know for sure, but I don't think they're open source. Yeah, the next question is about if you received the presentation after the webinar. Yes, this presentation has been recorded, and you will also get access to the slides. So you will have a link to all the papers that I mentioned. The next question was, is there any robust established algorithm to get the distortions and radar shadows? And how can we utilize it for our study? Yeah, I would say for distortions and radar shadows, there's quite good algorithms for doing this in any kind of standard SAR processing package. The most important thing is that you have a good digital elevation model to get the distortions and radar shadows right. In our case, we are fortunate enough to have access to the Copernicus global elevation model at the grid spacing of 30 meters. That already gives you very good results. And if you, for example, use that data set together with an open source software like Snap, you can get very nice maps of radar shadows and distortions. I think overall as a generic statement is that the SAR community is working towards improving the definition of those SAR backscatter images to get rid of topographic distortions as much as possible. There will always be areas in very steep topography that you cannot get out. But with, say, the improved way of radiometric correction of topography, that was that's now known as the terrain flattened gamma images. You get out weaker undulations very, very nicely. I hope I'm clear. Then the next question is, hi, with GLOFAS, can you look at historical images, free to use for anybody around the world? And thank you for the comment. Yes, the images are in GLOFAS. So we recently done a reprocessing of the complete archive. So I hope if you go through GLOFAS in there, you will find all of them. There's also another user interface that I haven't shown, where you certainly get all the images. So these are now available. The next question is, why can't the sensor on the Sentinel-1 satellites be switched on all the time? Is it because of power limitation? Yes, that's exactly the reason. Because the SAR instrument requires quite a lot of power to operate. Basically the power that is coming from a solar panel is not enough to operate 100% of the time. Such modern SAR systems that also offer such a high resolution, you need to send many short pulses down to the Earth, and every pulse obviously requires some energy. So this is the reason. And the coarse resolution of the ASCAD data, where I can switch on the sensor all the time, obviously, you know, it's a trade-off between spatial resolution and temporal coverage. And then the next question is, why don't we have synthetic aperture radiometers? Well, actually, SMOS is a kind of synthetic aperture radiometer. Say it's a bit difficult to explain. Synthetic aperture radars can rest on the technology, can rest on the feature of microwaves that are generated by the radar. That these radar waves are very coherent, meaning that we can compare phase measurements. So in that sense, a synthetic aperture radar is per definition almost a coherent measurement system. On the other side, a radiometer that measures the naturally emitted radiation is almost per definition not a coherent measurement system. So talking here about a synthetic aperture is kind of, seems to be a contradiction. No, but what the SMOS mission is doing, it more or less looks at correlations of phase, of the coherence of noise signals from the ground, thereby being able to simulate a larger antenna. But it's a very complex question. I don't think I've answered it too well. So yes, it is, but it's more complicated. Then the next question is, why does rock below soil have strong backscatter? The dielectric constant is just as low as soil, right? Yes, you're right. The dielectric constant of rock is not too different from soil. So that's not the distinction. The distinction becomes because rock often has a much rougher surface than the soil or the sand. Yeah, let me go back here on the slide and just show you here, say, the backscattering signals from the desert areas. So there's areas of very high backscatter, and then there's areas of very low backscatter. This is essentially those areas of high backscatter. These are rocky or stony surfaces where there's, you know, very rough surface for the radar. Then intermingled with deeper layers of sand where the radiation is being swallowed. The next question is, well, thank you again for the nice comment on my presentation. So you're wondering if you can use Google Earth Engine to generate maps. Yes, I mean, Google Earth Engine is a very powerful tool for doing an analysis and working with the level 1 data. And I think it's by far the most used platform for doing free analysis of Sentinel-1 data. Say from my perspective is they do some of the pre-processing steps in a not optimal way. Yeah, so I'm not too, as an radar expert, I'm not too happy with everything they're doing. And the way how we use the algorithms, we also wouldn't be able to implement the algorithms easily on the Google Earth Engine platforms. So many approaches can be extremely nicely implemented on Google Earth Engine, but not everything. Yeah. So I think more straightforward image processing techniques can be nicely implemented there. If it's more complex processing, yeah, you may struggle. On the other hand, I mean, also Google is of course developing the platform further, and yeah, and if you're a power user, they also may help you with some of the implementation. But say again, for us, it's also we don't work on Google Earth Engine, but we have developed our own cloud computing facility connected to a supercomputing facility, simply because we don't want to become dependent on Google, but have like our own European capability for analyzing the data. The next question is, what were the input parameters for soil moisture retrieval? Is there any field parameters were utilized, like roughness, etc.? For the soil moisture retrieval, as for the flood mapping algorithms, we try to use auxiliary data as little as possible. Yeah, our approach is that we look into the historic time series and learn already a lot about the backscattering behavior for each pixel from the data itself. So in that sense, the use of auxiliary data is rather limited. And so the retrievals are closer to the satellite data, and basically be less dependent on those auxiliary data. You know, if you look nowadays on what many people are doing, they use model soil moisture data, and then they use the satellite data, and then they use a machine learning technique to train the satellite data to look exactly like the model. Then the results are very dependent on the model results. So the data, the retrievals may look very nice, but they don't contain too much information from the data itself. So there's always, well, difficult decisions you need to make on how you train your models. Obviously, without auxiliary data, you cannot train the algorithms. There's always some external knowledge you need to bring in, but if this external knowledge becomes too much, your retrievals may become useless or not too informative. Yeah, the one question you said, particularly on the roughness. No, we did not use roughness in the retrievals, simply because there is no data set on roughness. It does not exist. So roughness becomes a model parameter that is, you know, may have a physical basis, but it's essentially an effective model calibration parameter. And the one important assumption that most algorithms do is that roughness stays constant within the time period considered. So at the coarse resolution of the ASCAD, that assumption is for most of the world quite valid. If you work at very high resolution for Sentinel-1 at the field scale, obviously that assumption breaks down if farmers manage their fields. Yeah, so it's again a trade-off between the spatial scale and the model that you're using. As a general rule of thumb, the finer the spatial resolution you're working at, the more complex your model would have to become, because at a very fine scale, more and more phenomena are obvious. If you work more on a coarse scale, things, you know, local phenomena may not be as dominant at the coarse scale, and then it becomes easier to select the model. The next question is, on the GLOFAS, you showed on a slide there's an observed flood layer that's not appearing on my end. Oh, I'm sorry for that to hear. No, I don't think I have a particular privileged user account. maybe the problem is, let me try to have a slide here. In order to switch on this layer, you need to go to this monitoring here. And when you go to the monitoring here, you see the flood layers. And once you have this switched on, these GFM layers should start appearing here. I hope that works for you as well. The next question is, can you please provide the right approach of pre-processing of Sentinel-1 data for soil moisture? Well, I think in terms of the pre-processing, to have like an analysis where the data set, we know quite well how to do this and what is required. So to process the SAR data, the topography needs to be taken care of, both in terms of the geometric calibration and the radiometric calibration. I think scientifically the methods are there. It's also implemented in toolbox like SNAP. The problem is for many applications that if you do the full topographic correction, the processing can take very long time. Yeah, if you want to correct a Sentinel-1 data just for the geometry, then the processing, for example, on our machines takes about 20 minutes per scene. If we do the full radiometric terrain correction, it may take you 5 times as long. So if we now have then say the task of processing thousands of images, as we do typically, then it makes a big difference if the processing of one image takes 20 minutes or 1.5 hours. So we still normally stick to the approach that we have just geometric terrain corrected images. But we obviously also have been intensively working on finding ways of how to improve the efficiency of the processing. And right now we're writing up a paper where we show that the processing can be sped up significantly by exploiting the fact that the orbit stability of Sentinel-1 is really excellent. So we are very hopeful that, say, within the next year or such, we will be able to process the Sentinel-1 data on a global scale with all the necessary pre-processing steps to have the best possible backscatter product before going into the soil moisture retrieval. For the soil moisture retrieval itself, I wouldn't say that there's the best one standard, but there's different modeling approaches. And our experiences are that you can have different approaches, and many different approaches can work equally well. They don't work equally well in the same way. Obviously, different approaches have different strengths and weaknesses. But if you do an assessment of the quality of the products, you can have 3 different algorithms, and all 3, if implemented well, compare the same. Yeah, for example, we have compared pure machine learning techniques with like quite complex physical models or semi-empirical models. So as long as the information is within the data, you can choose different approaches to do it well. In our case, we still like to work with the rather simple change detection algorithms because from an operational point of view, they have the advantage that we can look into the algorithms and we can check step by step what the algorithm is doing. So it's not like with the machine learning technique where you have a model that kind of does all the magic and you get a result, but you don't know why you get the result. For the change detection algorithm, you can follow this step by step. So from an operational point of view, for us, the change detection algorithm is the transparency is the advantage. But obviously also there we start to integrate more machine learning steps into the algorithms as we did in the past. So obviously these tools start to become very powerful, but we always try to still, keep a physical understanding and keep different processing steps so we can monitoring the results. The next question is, can you share the techniques for flood mapping? Yeah, send me an email. I mean, we are happy to share. I'm not sure how much we have published open source, but yeah, if you send us something, we are happy to share some of the code we're having. We do our code development in Python. So if you're proficient in Python programming, it shouldn't be any problem. And the next question is, okay, just two more things, messages. So I think I've seen all the questions and I hope I answered them. I didn't type the answers, but just described them. Can I ask around? Is there any more questions? If you want to pose a question when talking, I can also give you rights to talk if you wish. No, I don't see any more questions. Yes, Diana just posted the message that the webinar will be on the YouTube channels in the coming days. So if I was too fast or not, you didn't understand immediately what I was talking, you can rewatch it. So thank you very much for everybody to attend and staying with me, and also many thanks for the very good questions. I wish you a very nice day. Goodbye.